There we are. Excellent. So, title, Much Ado About Nothing. Truth to be told, this talk is in honor for all you guys working hard and inspiring to do brilliant physics. So I might as well have called this talk for Much Ado About Everything rather than nothing. It's partly a story of what got me interested in mathematical physics, in particular theoretical physics if you prefer. But it's also a story of life in general, and perhaps the way science and perhaps physics in particular sometimes works out. And when I say sometimes, I rather suspect it happens so more often than we like to admit. So, much ado about nothing. We're gonna follow two basic ideas. They're both completely essential to physics, especially the first one. Same equations have same solutions. I'm sure you found that with your exam questions today, that there's something that you may never have seen before, but lo and behold, it follows. It shows that the laws of physics turn out such a way that it follows an equation that you have seen before, and you understand it, you know exactly what the solutions will do. Same equations have same solutions. We only ever need to solve anything once and the rest will follow. So a typical example, we have say a system of rabbits or foxes eating rabbits eating daffodils, which is exactly the same as one radioactive decay going into another radioactive substance decaying into another. Different systems, same equation, same type of solutions. And the second principle is that good ideas have unintended consequences. So this is a more dubious as a principle in physics, but life does tend to work out that way. It's not uncommon that one spends a lifetime pursuing a particular idea only to find that it ends in a dead end, or there is an experiment, perhaps by one of you guys, who proves it completely wrong and meaningless. And yet, at the same time, someplace completely different, a different field of not even physics. It could be that this is exactly the missing piece of a puzzle that they've been looking for. So something that you're disheartened by turns out to be pure gold in a different light, in a different context. So this is the beginning of the story I'm going to tell you. So I'm going to illustrate that on a story that started over 2,500 years ago. And don't worry, we will very swiftly come to modern days. It will end, or perhaps not end, but it will take us to the state-of-the-art, cutting-edge research of today. So following these two principles, bear that in mind. Here we go. In the beginning, let me introduce this grumpy old sod called the first mathematical physicist as we know it, Democritus. And this is what he said: by convention sweet, by convention bitter, by convention hot, by convention cold, by convention color, but in reality, atoms and void. What a profound thought. This wonderful, complex nature, the world that we know so well, in reality there is nothing but, and here comes the two revolutionary ideas. The idea one is it's all about matter. It's all about what is, and that what is he calls atoms, something you can't divide into smaller pieces. And the second, even more revolutionary idea is that every bit as important as the what is the what is not, and that what is not, this void, is just as real as the what is, which is the matter that he calls atoms. So that was a long time ago. We have moved on quite a bit since. However, swish, a couple of thousand years later, if we go to Dalton, 1808, He's a chemist. He used the ideas to explain how elements join together to make compounds. So the idea of atoms was very much in his mind. And similar times in 1830s, Faraday was fascinating by the void, and he was imagining a complex nature in this structure, in this void, this nothingness, because he could see that there was gravity, there was electromagnetic forces that were affecting matter. It was visible that they had an effect on matter, and yet we couldn't see this void or this medium where all these things were happening. And the winning idea at the time was that the void was indeed a complex medium. It was called ether, which filled the empty space surrounding everything. And this is what they believed was that what is not, as Democritus would have put it. And the next question, once you have an idea of ether, is what is this what is? What are those atoms, the matter that we indeed can see? And that took us a little bit later again, sort of Victorian times, to through a very bad habit. I do apologize, but this was before smoking was dangerous. And as you can see, a lot of wonderful, brilliant ideas come about from observing everyday phenomena, and playing a light bulb lights up and something happens. So I can only speculate that Lord Kelvin, when he was smoking his pipe, just like we can see here, Gandalf is smoking pipe, Rock Hudson, there is this volcano Etna, they create smoke rings, and smoke rings, it looks like once they're formed, they keep their shape. In a sense, the idea is that if we can visualize, and we can, it's obviously taken here on a photograph, smoke rings as stable objects. They even made experiments when you can let two smoke rings go through each other, and believe it or not, they don't lose their shape. They go through right each other and come out as two smoke rings as entered. So very stable. And if you can imagine ether now, then why not imagine the matter, the atoms, as vortices in that ether? So that's the smoke rings gave raised an idea to Lord Kelvin to begin with, and he chatted to his best friend Peter Tate, and together they started working on this idea. What if matter, the atoms, are indeed stable structures inside that ether that surrounds everything? So atoms inside the void. They spent tremendous time, about 30 years they were working on this, developing this idea, because if you can have one circular structure like a smoke ring, and you can see they have, for publicity reasons, they've moved away from real smoking. They've got a smoke machine here just to demonstrate to the scientific community the brilliance of their idea. Then you can imagine more complex structures other than just those donut-shaped rings to illustrate different types of atoms, because by then they already knew they had the periodic table, not all the elements, but plenty elements to know how the structure works and to see how the elements get more and more complicated. So they needed, so having different knotted structures, when you can create more and more complicated knots, is quite an attractive idea, in hope to describe all the elements in periodic table solely by looking at different knots. So in 30 years, for many of us, that's a lifetime's work, especially for Professor Tate. He was a professor in Edinburgh, I should perhaps add, so there's a local connection here as well. And he was working hard, he was classifying, he was doing his very best to understand how to construct systematically a table of knots. So he counted their different crossings and how you can make sure that you're not double counting, so the same knot just looking different, was indeed the same knot and not something different. So in 30 years, was it 2 or 3 papers published in Royal Society of Edinburgh, and everything was looking absolutely marvelous. He looks a bit tired, but he worked hard. And okay, I should perhaps mention that when I say he was classifying knots, he was working with mathematical knots. So that's the lower picture. The physical knots that we all do when we do our shoelaces or inadvertently get into our earphones, they have open ends. So that's the first difference. Whereas a mathematical knot is always considered as a closed structure. So a picture here is a trefoil knot, and the upper picture, the physical one, and the lower picture is a mathematical knot. The other thing with mathematical knots that we don't need to worry about, and Tate was not worried about it, is all the physical properties like thickness or friction or anything that we associate with physical knots. So it is just the knotted structure, something that you cannot undo by simply slipping rope around or through each other. If cutting it open is the only option, then we have a true knot at our hands. So the elementary table, I don't think I have a picture of that, but there is a fabulous original drawing of Tate's proposal for the periodic table, where all the elements were presented as knots. Because the knots are stable, there is vibration property, and the many types of atoms, the way they thought of atoms, could be represented by different type of knots. So extremely attractive idea to have atoms as knots in the ether. So they weren't doing mathematics, they were doing physics, and they thought at the time that this was revolutionary, cutting edge physics. They were going to sort out once and for all how all these things work properly from very, very first principles, sort of fundamental properties of matter. Until, as you can see, something happened 1887, even before the full work was done, so it must have been completely heartbreaking for Professor Tate. Michelson-Morley and the experiment, and once and for all proved there is no such thing as ether. You knew this was coming because obviously all that was just the olden days ideas, and we know very well that it didn't quite work out that way. Physicists are not a very huffy lot, so we moved on. But I should perhaps mention that where I'm sitting right now, this building is named not after Professor Tate, who was indeed a professor in Edinburgh, but it's named after James Clerk Maxwell, who was not a professor in Edinburgh at any time. So there was slight embarrassment there, I'm sure. I wouldn't say that, there was a little bit of embarrassment, but more importantly, the momentum was lost. I mean, having an experiment that proves that some theory that you've been working on is utterly and completely wrong, and utter nonsense even, is quite devastating. And this is a wonderful thing about physics. It doesn't matter how brilliant your idea is or how brilliant your theory is. If an experiment shows that it is wrong, then the theory is not worth the paper it's written on. So there was definitely momentum lost for about 100 years when nobody in physics went near those wonderful ideas of knotted structures. At the same time, remember I did promise you unintended consequences. Mathematicians independently, they were working on a new field called topology. So that's a study of geometrical properties and spatial relations unaffected by the continuous change of shape or size of figures. So the image here, and I tried to bring this a Christmas theme to it. So we have an orange, a chocolate bar, and a tumbler. They topologically are identical because you can deform one into the other by a continuous change. So those represent, this is the Christmas bubble example. I have a Christmas wreath example as well of the same phenomena when you can continuously transform a donut into a coffee mug. Okay. So this is an independent field, different people, different interests, different ideas, working on a new field called topology. The way they approached it was, rather than follow in Tate's footsteps, although Tate was sort of their hero because he did it first, they used a formalism called invariance, not invariance, to help them classify knots. And again, I won't give you the full story. I'm going to just mention one of the knot invariants. So invariant is something that remains the same, even if you change the shape a little bit. Like in the picture below, we have an unknot, this sort of donut-shaped knot. And if I just twist it once and twice a little bit, I won't actually change it. It looks very different, but you can see just by following the lines that indeed both images represent exactly the same simple loop O. Now, the whole idea with having knot invariance is that different knots have different knot invariance. If there is a mechanism, an algorithm to calculate it, then however difficult the knot looks like, and I'm pretty sure I have a picture of a more difficult knot. Oh, here's a picture of a more difficult knot. Google says that this is also a picture of a unknot, a simple loop O, believe it or not. But to work it out, having an algorithm that simplifies it and allows us to calculate a knot variant, and if that knot invariant is exactly the same as for the single loop O, then there is no doubt that complicated tangle indeed is the same as an unknot. So that's the power of having a systematic way to calculate knot invariance. Equivalent knots have the same knot invariant, but two different knots can never have the same knot invariant. It's a very foolproof way to catalog knots. Here's another example of a trefoil. Again, three pictures, they look very different, but they all represent the same knot. So the knot invariant that I want to talk about, or mention at least, I won't talk too much about it because we're all physicists and this is now maths. So this is totally 100% maths. It's 1980s, so we're almost in modern times. Well, it's modern times for me. I'm not sure how many of you were born in 1980s when Jones invented his polynomial. And in particular, he calculates a number that Jones is invariant called JK, K for a knot K. And in this convention, the unknot has Jones's number 1. And if the knot is not 1, then it has a more complex structure. It cannot be untangled to turn it back into a donut. And different Jones's number, of course, means different knots. And the system is ingenious. So in a sense, it reduces us to doing maths with pictures rather than with symbols or numbers. So there are three different knots or sort of elements of knots that he considers are the crossing, which goes either this way, so it's a K plus, goes up, K minus, goes down, or doesn't cross at all, which is a K knot. And there's a magic formula when you can choose any numbers. So we can call it alpha, beta, gamma if you like. I put in 3, 5, and 7 just because I like odd numbers. But you add them up, and for any knot you have this identity. It adds up to 0, which is a remarkable result for any real knot. And the key is that you consider strictly only these 3 possible ways of either crossing or not crossing at all strings. So if you have, so the big picture to the left is not a knot because we don't have in order to turn it into a knot, we simply replace the mystery box with any of the 3 pictures to the right. And likewise, you can see wherever you meet 4 ends of a string, you draw a circle around it and you identify which one of those 3, k plus, k minus, or k naught, we have there. And this way, this is sort of schematically the way you calculate Jones's invariant for a knot. So you start with a complex structure, doesn't matter how complex, and systematic way, you untangle it mathematically by identifying those 3 k's, and this way you end up finding or calculating the Jones invariant for that particular knot. Goes without saying, the system is robust, so it doesn't matter how you prefer to do this calculation, in which order, or how you identify all these boxes, you get exactly the same answer every time. Okay, so this was all math. So what has that got to do with physics? Well, as always, everything and nothing. If you think of quantum theory, well, let's think of classical theory first. You have particles in point A and B. If a particle goes from point A to B, according to Newton's laws, it follows some trajectory, one classical trajectory. Everything is simple and straightforward. Quantum particle can follow any path between points A and B. So it could have a path quite similar to classical path, or it could wiggle around in any possible way. It can go forwards, backwards, do swirls. It can have a knotted path. In time, you can see it's the 2 spatial dimensions, the drawing, and the 3rd dimension is the time. So the relativistic quantum particle travels in space-time, and I've just drawn a few possible particularly wiggly paths that they may take, because Feynman says that it can take any paths of any shape, and if Feynman says they can, they do. So because of that, we are approaching this idea of introducing, in a roundabout way, we're coming back to knots, not the way Tate intended, but kind of through a back door. The one issue we still have is dimension. So classical knots, they exist in 3 dimensions. Well, it's obvious. You try make a knot in 2 dimensions. You don't have enough dimensions to loop through. So we need a 3rd dimension in order to make a knot. On the other hand, if I have 4 dimensions, then my knot can just vanish. It can escape into the 4th dimension and untangle by leaving the 3 dimensions where I had this knot fully under control and fully knotted. It can untangle to the 4th dimension. So 3 is a absolute requirement to sensibly talk about knots. And this is okay, because as we saw in the previous picture, we have a space-time. So if I visualize the path in 2 spatial dimensions, then I get my 3rd one to allow knotted structures through time. So this will work. So 3 equals 2 plus 1. I told you it would be a light-hearted entertainment. This is perhaps not the mathematics you were dreading, but it's an extremely important equation. So in 2 plus 1 time dimensions, we can describe these paths allowing knotted structures. What's that got to do with knots and topology and Jones's polynomial? Well, quantum theory. So it's all about possible paths. We have to sum over all possible paths. And if there is let's call a path for k. I know, but amuse me. We call a path, any particular path k, then there is a probability amplitude associated for this path, and the amplitude is entirely dependent on the path. So you can see that some paths are more probable than others, and it all depends just how wiggly, how complicated, how knotted those paths are. The probability amplitude for a given path k is in quantum theory given by the Wilson operator. And if a knot k is regarded as a space-time orbit of a charged particle, then the Jones's invariant for that knot happens to be the average value of the Wilson operator. Now, how about that? Coincidence or divine intervention? Who knows? But it's a remarkable result in its own right. So all this work that Jones did, classifying different knots, identifying a way to calculate a unique invariant that he calls the Jones's invariant, turns out it has a real physical meaning, and it's the average value of the Wilson operator that gives us the amplitude, the probability amplitude for a given path k. So I don't remember if you recall, I had this magic formula written out for any given knot with those random numbers. Well, in physics, those seemingly random numbers, they're determined by the charge of the particle and Planck's constant. So again, we have something that's seemingly abstract and pure mathematical result that turns out to have a real physical meaning. So this is all very well because we are still, I mean, this is a fantastic result. I don't want to take anything away from it, but we still have a slight problem because that was from 2 + 1 dimensions and we live in 3 + 1 dimensions. So we have conventional knots in 3 spatial dimensions, and then we have the time on top of that. So can we scale up Jones's invariant to higher dimensions? I mean, since I asked the question, in fact, I answer it straight down, yes, we can. And now the scaled up is inverted commas because actually scaling up wasn't so easily done. It was Kovanov, as recent as in year 2000, he had to invent a whole new theory, a much more sophisticated theory than Jones's, because it wasn't just a matter of quickly scaling something up. They actually he had to work quite hard because ideas are sometimes more simple than the actual technical resolution of it. But he did, and he was successful. It's called Kovanov's homology, highly non-trivial. He treats knots as physical objects, so we've got the dimension sorted. Again, there is an explicit set of rules. The explicit set of rules are rather complex. I think you need to be well versed in topology to attempt to follow these rules. However, they are 100% mathematical, so that Kovanov's homology does not require any physics or quantum physics to work. However, knowing quantum physics helps us understand what he actually did and how it all works. So this is in many ways an absolute triumph to mathematics and physics working together. So the main difference is that Jones's invariant is a number, whereas Kovanov's homology is a vector space. So there is already a step up in complexity. And if K is a knot in 3-dimensional space, then Kovanov's homology is the space of all possible quantum states. So again, we have something mathematical and abstract, and there is a real physical meaning attached to it. So this is sort of where we're going to end the story, or perhaps I should say it's not the end. This marks the very precise beginning of a new era when new talented physicists take over, where Lord Kelvin and Professor Tate started all these years ago. Many of you have heard, and some of you probably by me, that knowing maths is essential to a physicist because maths helps us to express physics in a more concise and precise way, and thus helps us to understand physics better. It's not every day that we hear the opposite, that knowing physics, and perhaps quantum physics in particular, helps us to understand maths better. So I'm delighted to be able to bring that point in as well. So here's my third guiding principle to this talk. So knots, easy to imagine, hard to do. I don't know whether you have thought about, well, perhaps you have. It's inevitable when you study physics. You can't help but think about nature and observe nature and come up with ideas how things might work. And some ideas are absolutely brilliant, especially when you chat to your friends, like over this weekend when you meet friends all over the world. And the later the night, the more brilliant the ideas seem. But what you find quite soon is that to bring those ideas and put them on paper and develop them so that they make sense and form part of an existing understanding of physics is much harder to do. So what people have done in the past couple of 100 years is truly remarkable. And the latest development with like Kovalov's homology is again a truly remarkable theoretical triumph, I would say. So having an idea of how to do four-dimensional knot, so we have a three-dimensional real knot and the time added to that, is a fantastic triumph, and it will allow us to explore more adventurous ideas without feeling vulnerable to experiments or counter arguments and suffer the same fate as Professor Tate did 100 and odd years ago. So the areas where, I mean, I'm no particular advocate for knots in physics, although knots in physics is a new exciting area of research, especially in biophysics. The DNA strains, the tangles in biology is very exciting area of research. In particle physics, I know they tried to construct periodic table with knots, and that didn't quite work out. At the same time, we have fundamental particles, we have quarks bound together by gluons. Might there be a knotted structure in the underlying mechanism? Who knows? We need you guys to be brave and imagine wonderful, outrageous things, and then having the confidence to sit down and work it through. And a lot of work has done, so you wouldn't be starting from scratch. Another thing, of course, with the knotted things, I've tested the number of dimensions. I was just wondering, what did I mean by that? Well, because knots, the physical knots, strictly live in 3 spatial dimensions, if you can find a knotted structure that is stable as a solution to your equations of motion, then if it's there, then we know that we are indeed in 3 spatial dimensions. If it's not there, then we don't know very much, but we start wondering about the number of dimensions where we actually live in. So it's another exciting alleyway to go down in and see whether that turns into an avenue. So you've been all very polite and very quiet. It's the most bizarre experience to be talking to a screen in my office, whether my time is up or how we're doing. This is more or less what I wanted to tell you, as we are all behind screens. I'm not going to attempt to do any experiments. So this is the end, or possibly a new beginning, and I'm more than happy, delighted to take questions if there are any.
Thank you so much for this amazing talk. So yes, now it's time for questions. Please raise your hand or type in the chat box if you have any questions. And I will start by one. So you mentioned the physical knots like the shoelace and the earphones. So basically, my question is, what exactly makes a knot more stable than another? Is there any key factors or properties?
Um, do you mean a mathematical knot or a physical knot?
The physical knot.
For physical knots, we have, besides the structure itself, we have there is friction. So if you use a different material, then of course the knot is much more easy to untangle if it is possible to untangle. Earphones is a good example. You have plastic wire, which is, the friction is it's less of a friction than if you can think of a more sticky material, and you can sort of just slowly loosen it up and see, identify the fake knots and the real knots. And the fake knots you can just untangle, and the real knots you need to do something more. The other wonderful thing with knots is that you get already amazing structures just with a ring, with a donut shaped, which has seemingly no structure at all. If you tie a rope around a tree, for instance, you do it once, you do it twice, that the friction between the rope and the tree grows exponentially. So it takes very little structure, just one O-ring, and so it's full 2 pi around the tree. It's a very stable structure. You can put a tiny person in one end and a massive ship or something in a rough sea on the other end, and that's usually enough to hold it steady because of the friction that creates between the rope and the tree. If you think of a physical structures, then there are a lot of amazing properties already with very, very simple structures. You don't have to go beyond too much to find very stable and interesting structures. For the mathematical knots, of course, I mean, the amazing thing is that the Tate catalogued, I can't remember how many, but there was like 30, 40 odd knots going more and more complex, and they were all different. And since then, people have tested, because we've got computers, we've got luxury of technological aids to do the calculation for us. And guess what? They didn't discover one single error. So he did with paper and pen in candlelight with great patience, and he made no mistakes cataloging his knots to very, very, I mean, seriously complex structures. And of course, the more crossing, the more tight, the more stable, if you like, the knot is.
Okay, so there's a mathematical model that can like predict the stability of the knots.
I mean, all knots are stable. This
Okay.
is the one attractive idea that makes this idea so attractive.
Okay.
All knots are stable. One way of looking at knots, you can sort of think outside the box and see knots in a two-dimensional, like a computer screen, which is this plasma screen. If you have a defect, say there is, everything points up, but then one particle points down, and there is no way to undo it. It's kind of stuck. The defect is stuck there. So that's another knotted structure, if you like.
Okay. Yeah.
So yeah.
Yeah. Thank you. Okay. So just yeah.
I can see a hand up.
Yeah, Osama, I'll just unmute you.
Okay. Hi, and thanks for the wonderful talk. It was very enjoyable. But I have one little gripe on the description of Jones polynomials and not invariance in general. Since I have familiarized myself a little bit with these not invariants previously, and as far as I've understood, the not invariants only only like guarantee when two knots are not the same, but there are some different knots with, for example, the same Jones polynomial. So we don't have this kind of like foolproof test to test whether two knots are the same. This is at least what I have read.
I can't really comment on to that level of detail. So sorry, I missed the logic of it. So yeah.
I mean, like for example, it's to me, it's an open question whether there exists a knot that has the same knot invariant or the same Jones polynomial as the unknot, for example. These kind of questions are still open, like so, in mathematics.
So if the knot invariant is something other than 1 for Jones's number,
yeah, then we know that it is a knot. But if the Jones polynomial gives us 1, then we cannot tell whether it's not or not.
If it tells us 1, then it is an unknot, surely.
It's not surely. Like, this is an open question.
Oh, I would not consider it as an open question.
Yeah, but at least I've read that there is no proof for it. Like, we don't have actually any like guaranteed tests for general knots to check whether they are unknots or not.
Right. I don't think I have quite worried about that, to be perfectly honest. I think my approach has always been to be as open as possible and not worry too much about things that have not 100% been proven. I mean, that's part of what mathematical physicists do. We try to be as open as possible to push the boundaries and see where the ideas take us.
Yeah.
And see the value in that. And then we sort of trust the experts, the mathematicians, to at the same time work out all the details.
Yeah, but I just wanted to say that maybe it would be good put some kind of remark that we don't actually know whether it's true. And if I remember correctly, there are actually two different knots with the same Jones polynomial. Like those kind of examples, I think, have been found.
Yeah, it wouldn't surprise me. There is nothing that an exception to confirm the rule. I'm very impressed that you have already familiarized with knot theory. That's very well done.
Yeah, thank you.
Thank you, Osama, for your question. And also have another question. Trong? Yeah.
Hello. I think there was another question before me in the chat. Maybe you want to address that first.
Sorry, who was the speaker?
Okay, sorry. Maybe if you don't mind, I will post my questions.
Yes.
So, could you help me understand one of the few equations that you had in your slides? So I'm talking about the Jones polynomials, JK equals to average value of the Wilson operator. So I'm thinking of comparing between the unknots, which I believe the Jones is just 1. And let's say the trefoil knot, which is T minus K minus K cube, or yeah, but it's non-trivial. So if I were to translate that to the Wilson operators, what will it mean?
I don't think I can help you with that level of detail today, but I would strongly encourage you to pursue that path in a quantum field theory course.
Okay, thank you.
Shall I read the questions in the chat?
I'll read it for you. Yeah. So there's a question. Does every topological field theory in 3 dimensions yield a knot polynomial like the Jones polynomial? I read that it is the case for arbitrary Kern-Siemens theory, but how about more general TFTS?
It's true for the Chern-Simons theories. For the general theories, as always, to imagine it is easy, to prove it is difficult. So there is a particular type of a mathematical action, which is, I would say, very general and typical to most quantum field theories, that does allow knotted solutions. So it starts with, the simplest one is just a donut that you, before closing the ends, you twist it once, not like a Möbius strip, but you twist it 2 pi and then glue pieces back together, and you can show that like in QED, quantum electrodynamics, that theory supports existence of such solutions. And again, to show that these days you can do some things analytically, but largely this is all shown by numerical calculations. You start by modeling your solution. You take the simplest knotted structure and you plug it into the box of partial differential equations of your theory to show that it indeed supports the existence of such solutions. I mean, the theories that people have proven is they show that it's not ruled out that such knotted structures exist.
There is another question. So tapping on stability cannot appear somehow in field theory, be it classical or quantum, related to solutions to systems with topologically non-trivial structure?
Yes, is the answer. And indeed, people have been trying to explain a wide range of phenomena with knotted structures, like the solar corona, the plasma that surrounds our sun, and the black spots, to see whether could those be knotted structures, because they're very stable, they're localized, they could measure the energy. And there have been phenomenological models come forward to see whether knotted structures could explain those sort of phenomena. And again, to do that from first principles, from proper pure theory, that is much harder. So there's again a difference between theoretical physics and mathematical physics. And theoretical physics, in some ways, it's easier to work with and explore. Whereas in mathematical physics, we are very much constrained, and we have to do things properly, and that becomes very hard just because the equations are complex and the solutions are complex. Not impossible, though. It just takes someone bright, young, and ambitious, very much like you guys.
Okay, so just a reminder, if anyone has any question, please raise your hand.
There is a mention of solitons, and you are absolutely right. There's an extremely strong correlation between knotted structures and solitons. The solitons are another non-dissipative solutions. You have the stability, and you can't undo them by just continuously deforming or changing them. So it's a very strong correlation between solitons and knotted structures. And this takes you, once you open your mind to, you go from one idea to next, you go from donuts to soliton waves. It opens up a whole new area of physics where you can have rogue waves, tsunamis. You can have optical solutions, optical solitons, when you can send a signal through a wire without losing its intensity for enormous distances. Black solitons, which is the absence of solitons, which are even faster than solitons. So it opens up a whole new area of physics, and they're all connected.
Any other questions?
So if there are any other questions, we have the Meet the Speakers session at 6 p.m. today. So you guys can just keep your questions for then. If there's not anything else, then we can move on to have a break for 15 minutes and you guys can join us at 4:45 for the next speaker.